All right, line of symmetry and rotational symmetry. Line of symmetry should be something you kind of remember, because the line of symmetry is when it's a line that divides a figure into two reflections, I'm going to say, because it cuts it in half. You have two reflections on either side, and the reflections. Okay. All right, so a new vocabulary word that we haven't talked about, but we will later, is the word regular. When we're talking about shapes, regular means all the sides and all the angles are equal. But it matters because when you're doing a regular triangle, all the sides are equal. A square is regular, all the sides are equal. A pentagon, this one is regular, all the sides are equal. And a hexagon, all the sides are equal. So if all the sides aren't equal, that changes how many lines of symmetry there are. So if you're looking at the triangle, think about how many lines of symmetry you think there would be. And I'm pretty sure you knew there's at least one. Because this triangle has all the sides that are equal, you also could cut it in half that way. It's not quite in half, but you get the idea. And then you could also do the same thing at the other corner. That is not anywhere near in half. Anyway, they should all kind of meet in the middle, but you get the idea. So there's actually 3 lines of symmetry because all the sides are equal. If you had a scalene triangle, you wouldn't have 3. Same thing for the square. If you think about how many lines of symmetry there might be, there's for sure one going this way, and there's for sure one going this way. But because it's a square and all the sides are equal, you can also draw one diagonal. And then you can draw one diagonal this way. And so think about if you folded the paper, if you did this on your paper and you folded your paper along those lines, the 2 sides of the square or parts of the square would line up exactly on top of each other, which is a reflection. Okay, so a square has 4 lines of symmetry. All the angles are right angles, so it works. All right, a pentagon has 5 corners and 5 sides. And if you think about this, of course, would be a line of symmetry, which means because all the sides are equal, that every other corner you should be able to draw a line of symmetry which cuts the pentagon in half, and the 2 halves are mirror images of each other. So that means that every place where there's a point, I can basically cut it in half. And I should have, I need one more. Okay, so there's 5 lines of symmetry because all the sides are equal length, and so it cuts down the middle easily. All right, and then the hexagon, I hope you would guess would have 6, and you would be right. There's this one, of course, right here. And there's this one right here. So the points, the corners, I guess, connect to make lines of symmetry. And that's 3 of them. And then also, the sides make lines of symmetry. And there's going to be 6 lines of symmetry for the regular hexagon. So once my shape starts changing and everything's not all lined up pretty, same sides and same angles, there are way less lines of symmetry. So let's look at this next one. For sure there's a line of symmetry here. And for sure there's a line of symmetry here. You're going to be tempted, let's see if this works. You're going to be tempted to draw a line of symmetry right there, but don't do it. And it's hard to see without folding your paper. But if you did this, this corner would end up like right here, not lined up. This one would end up right here. So they don't really line up and would not lay on top of each other like a reflection. They would miss each other and it would not make a reflection. So this only has 2 lines of symmetry. Okay. The B has 1 line of symmetry. I'm going to assume that the bottom half and the top half of the B are the same size, which I think they are. But if you drew a B like this, with a big bottom half of the B, right? This one is going to have no lines of symmetry because if I folded this one in half, they would not be the same. So there's some letters with no lines of symmetry. Those are kind of the easy ones to think about. L doesn't have a line of symmetry. F does not have a line of symmetry. So there are letters and there are shapes that have no lines of symmetry. All right. Rotational symmetry is different. So, and it's a little harder to explain. Rotational symmetry means you rotate around the middle of the shape. And what you're looking at for is how many degrees until the figure looks the same. And it's hard to do on paper. It'd be easier to do with like cutout shapes. So before we look at example 2, let's do a little experiment over here with a square. And we'll pretend that that's a whole good square, which it may or may not be. There you go. Okay, so we're talking about having a point in the middle of the square that the square is turning around. So I want this corner to go down here, and by the time that corner gets down there, it looks the same again. And then this corner will go here, this corner will go here. You get the idea, right? Okay, so what I'm looking for is the angle that the corner travels to get to the next place where it looks like the same square. And you probably know that that's going to be a 90-degree right angle. I don't know why I didn't like it, but there you go. And remember that all the way around is 360. So if I turn a shape all the way around until it's back where it started, that's 360, right? So basically I have 1, 2, 4 places that a corner could stop, and the shape would look exactly the same. So what I do is I do 360 divided by 4, and I get 90 degrees, and so the angle of rotational symmetry is 90 degrees. I can do the same thing with a triangle. Oh, that's not good. See if I can make a triangle. There we go. Okay. Again, we're going to have the point in the middle that I'm rotating around. And if you think about this corner moving to here, this corner moving to here, and this corner moving to here, there's 3 corners or places where I could stop when I'm rotating, and it would look exactly the same. So I'm looking, in this case, I'm looking for the angle from here to here. So I'm looking for this big angle, which is more than 90. And if I find my purple, right, I've got 3 dots, 3 corners where I could stop and it would look the same. So I'm going to take 360 and divide by 3, which is 120 degrees, which is how much this angle is right here. So the angle of rotational symmetry is 120. I'm always going to use 360 to divide by, because I'm always talking about going all the way around until I get back where I started, which is 360. Okay, now I have this saw blade. Here's the middle, and apparently that's point K. Okay, we're going to ask, does it have rotational symmetry? And the answer is yes, because there are places where I could move my saw blade from here to here, and it would look exactly the same. So how many places are there, how many corners are there where I could stop and it would look exactly the same? Pretty much every corner or point, I guess I could say. So there are 12 places where I could stop and it would look like the exact same figure in the exact same place. So I'm going to take 360 because that's the whole thing, and I'm going to divide by 12 because there's 12 places where I could stop. And 360 divided by 12 is going to be 30 degrees. So this angle, the rotational angle of rotational symmetry, is 30 degrees. Okay, so now we're going to do both. And you need to remember when you're doing your practice to pay attention to if you're doing lines of symmetry or rotational symmetry, because they're different. All right, lines of symmetry for this star. It's looking pretty perfect. It's looking pretty even. I know I can draw a line right here. I can draw it, and if I could draw it through one corner, I can draw it through all the corners. Ooh, that was a bad one. Let's delete that one and try again. That's still not good. Okay. All right, so there should be 5 lines. When I'm talking about rotational symmetry, I'm talking about this point to this point. So I'm talking about this angle. I'm not stopping at each line. I'm just stopping at the angles. So I have 5 points over 360, and that's going to be 72 degrees is how far a point has to go around the center to look exactly the same. Okay. This next one does not have any lines of symmetry. And you'll be like, what? Typically, rectangles do not have diagonal lines of symmetry. because of the way the corners touch. They wouldn't be a true reflection. If it's a rectangle with 90-degree angles, then I can usually do one like this way. But you can tell from here that these two are not going to match up. So there really isn't any line of symmetry. Angle of symmetry, I would say these two guys. I can't stop at this little one because it's not going to look the same. Okay, so now I could do those two and do the same thing. If I'm going halfway around, that's 180 degrees. Okay. Side note. I'll do it in red. If you have to turn the figure all the way 360 degrees, then we say no rotational symmetry. Okay, if you have to go all the way around to 360, then you say no rotational symmetry. You should never write 360 for a rotational symmetry, because that's not a thing. It's kind of like -0. If you're in my class, you know that drives me crazy. Okay, so lines of symmetry. This one has a line of symmetry right here. And be careful with this one, because you might be tempted to go, oh, there's infinite numbers. But because of the dark lines that crisscross it, there are 4 lines of symmetry. And for this point, could go to here. There's 4 places where it could stop and look exactly the same. So we're looking for this angle right here, which if you haven't figured out, anytime there's 4, it's going to be a right angle. It's going to be 90 degrees.